Welcome back, everyone. We're diving into quantum physics today. We've got some excerpts from Quantum Physics in Minutes by Gemma Lavender, so get ready because this stuff is seriously mind-bending.
Oh, absolutely. Prepare for some serious aha moments. It's going to change how you see the universe. I can almost guarantee it.
I am so ready. Let's do it. So Lavender starts with something we all think we know, light. But get this, for centuries, scientists argued about whether light is a wave or a particle.
Yeah, like ripples on a pond versus tiny little bullets. You had Huygens over here saying it's waves, even proposing this luminiferous ether, this invisible stuff that light waves supposedly traveled through.
Right, like some cosmic jelly for light to jiggle in.
Exactly. But then you've got Newton, the one and only Sir Isaac Newton, backing the particle theory. He wasn't buying that ether idea one bit.
So who was right?
Well, that's the thing. They tried to prove Huygens right with this experiment, the Michelson-Morley experiment. They were trying to prove the existence of that ether stuff.
To prove light traveled in waves.
Exactly. But here's where it gets wild. The experiment did the opposite of what they expected. Totally backfired.
You're kidding? So they were trying to prove the wave theory and accidentally disproved it.
Pretty much. They thought light waves would act differently depending on how Earth was moving through the ether. But nope. Light speed was constant no matter what they did. Total mystery.
Okay, hold on. If there's no ether, what's light traveling through? Space is a vacuum, right?
That's the million-dollar question. And that's where James Clerk Maxwell comes in. He really cracked this thing wide open with his work on electromagnetism.
Okay, so from ripples on a pond to, like, electric fields. How does that even...
I know, right? It's a big jump. But Maxwell's equations, they were revolutionary. Among other things, they showed that electromagnetic waves, they travel at the speed of light. A huge, huge clue.
What are you saying?
I'm saying light itself could be a type of electromagnetic wave.
Wow, so light is an electromagnetic wave. That's huge.
Yeah.
And totally changes things.
It was a revolution. And you know what? It paved the way for an even bigger one.
Yeah.
The birth of quantum physics.
And that brings us to Max Planck, right? Lavender talks about him and this ultraviolet catastrophe. What was that all about?
Right. So classical physics, it just couldn't explain how light acted at high energies. Like, it predicted that this thing, a black body, basically something that absorbs all radiation, should emit an infinite amount of energy at high frequencies, which is obviously not true.
Yeah, that sounds kind of catastrophic.
Exactly, hence the name. So Planck comes along, and he's got this radical idea. What if, stay with me here, what if energy, instead of being this smooth, continuous flow, what if it's actually in tiny little packets? He called them quanta, and boom, quantum physics was born.
Okay, so you're saying that energy is like chunky, not a river, but more like Lego bricks of energy.
You got it.
Yeah.
But it's not just that energy comes in chunks, it's that the size of those chunks, those quanta, are directly related to the frequency of the light. That was the revolutionary part.
Hold on. I'm trying to put this all together. So light is an electromagnetic wave, but it's also made of these energy packets, these quanta.
Now you're getting it. And this is where Einstein enters the picture. He used Planck's idea of quantized energy to explain another mystery, the photoelectric effect. You familiar with that one?
Vaguely. It's when light shines on metal and makes it release electrons, right?
Exactly. But here's the thing, only light above a certain frequency could do this. If the light was below that frequency, it didn't matter how bright it was, nothing happened.
So it wasn't just about how much light there was, but the type of light.
Bingo. And that's what Einstein figured out. He said light itself is made of these energy packets, these photons. A photon with enough energy, meaning a high enough frequency, could knock an electron loose from the metal, like a tiny billiard ball collision.
Okay, so light is both a wave and made of particles. How is that even possible?
Welcome to quantum physics, my friend. And if that's not mind-blowing enough, get this. A physicist named Louis de Broglie, he asked this crazy question. He said, if light, which we thought was a wave, could act like a particle, could matter, like stuff things, could it also act like a wave?
Wait, you're saying that everything, even me, has a wavelength.
Hold that thought. We'll get there.
Okay, so we've got light acting like a wave and a particle, and now you're saying that matter might have a wave-like side too. My head is spinning. Where do atoms fit into all of this?
It's time to zoom in, way in, to the heart of the atom. And it all starts with, well, a bang, actually.
A bang, like an explosion?
Kind of. Lavender talks about Ernest Rutherford and his famous gold foil experiment. He fired these tiny particles, alpha particles, at a super thin sheet of gold foil.
Oh, yeah. I remember learning about this. Didn't most of the alpha particles just fly straight through it, like the gold foil was barely even there?
Exactly. That's what they were expecting based on this, get this, plum pudding model of the atom.
Pudding.
Yeah, the idea back then was that atoms were these mushy blobs of positive charge with electrons just randomly scattered inside like plums in a pudding.
Okay, I'm picturing it, but that's not what happened, is it?
Nope. Some of those alpha particles bounced back, some at crazy angles. It totally blew Rutherford's mind. He even said it was like firing a 15-inch shell at a piece of tissue paper and it coming back and hitting you.
Wow. That's a pretty intense reaction. So what did this mean for, the whole atom thing?
It completely changed everything. Rutherford's experiment showed that the atom wasn't this mushy plum pudding at all. It had a tiny, dense, positively charged nucleus right at the center.
And the electrons are orbiting around this nucleus.
You got it, like a miniature solar system.
But I thought there were some issues with Rutherford's model.
Sharp thinking. You see, if those electrons were constantly zipping around the nucleus, they should be losing energy and spiraling inward, eventually making the whole atom collapse.
Oh, right. Because they'd be emitting radiation as they spiraled in.
Exactly. But atoms are stable, thankfully. And that's where Niels Bohr steps onto the stage with his model of the atom.
Okay, tell me more about Bohr's model. How did he solve that problem?
Bohr said, what if electrons can only exist in specific energy levels? He imagined these energy levels as orbits around the nucleus, kind of like a staircase. Electrons can only be on one step or another, not in between.
I see. So they can jump from one level to another.
Exactly. And when an electron jumps between these levels, it can either absorb or emit a photon of light, a light particle with a very specific energy. And that energy corresponds exactly to the energy difference between the two levels.
And that explains why we see those unique colors of light emitted by different elements, like those spectral lines they use to identify elements in stars and stuff.
Exactly. Each element has its own unique set of spectral lines because each element has its own unique arrangement of electrons and energy levels. It's like a fingerprint.
Wow. Okay, that makes sense. So Bohr's model, big step forward. But it wasn't the complete picture, right?
You're right. It worked really well for hydrogen, just one electron, nice and simple. But when you start looking at atoms with more electrons, it gets a lot more complicated.
Yeah, that tracks. So where do we go from there?
Well, remember that whole wave-particle duality we talked about? Bohr's model, it still treated electrons like tiny little planets, with fixed paths. But we know that's not quite the whole story because they can also act like waves.
Right. Almost forgot about that. Waves, particles, it's a lot to keep track of. So how do we bring waves into the picture?
That's where things get really interesting and a little fuzzy. We have to dive into the quantum mechanical model of the atom.
Bring on the fuzziness. Hit me with it.
Okay, so remember those wave functions we were talking about earlier?
Oh, there you go.
Basically, in the quantum mechanical model, we can't say exactly where an electron is at any given moment.
You're saying it's like teleporting around, popping in and out of existence.
Not exactly. It's more like, imagine trying to pinpoint the exact location of a wave on the ocean, right? It's spread out.
Okay, I think I see where you're going with this.
Right.
So instead of these neat little orbits, we're talking about, what, blurry clouds of probability, where the electron is more or less likely to be.
You got it. We call these probability clouds orbitals. They have different shapes and energy levels, and they dictate the atom's chemical properties.
So instead of certainty, it's all about probability.
Welcome to the quantum world. And you know what's even wilder? This fuzziness, this inherent uncertainty at the quantum level. It might be responsible for some of the largest structures in the universe.
Wait, what? Hold on. You're connecting tiny fuzzy atoms to, like, galaxies. How does that even...
I know, right? It's mind-blowing. It all comes down to these things called quantum fluctuations, these tiny blips of energy that pop in and out of existence all the time, even in a vacuum. Sounds strange, but these fluctuations, well, they were kind of a big deal in the very early universe.
Okay, I'm officially intrigued. Quantum fluctuations, early universe?
Yeah.
Tell me more.
So picture this. A fraction of a second after the Big Bang, the universe is incredibly hot, incredibly dense, and quantum fluctuations are going nuts, popping in and out of existence everywhere. Now, as the universe expands and cools down, those fluctuations get stretched out, and that creates regions with slightly higher and lower densities of matter.
So these tiny random fluctuations are basically creating unevenness in the fabric of the early universe.
Exactly. And over billions of years, gravity does its thing. It's attracted to those denser regions, pulls more and more matter together, and eventually those denser regions, they become the seeds of galaxies, galaxy clusters, and this whole cosmic web we see today.
So you're saying everything, from the planets and stars to these massive cosmic structures, it all started with tiny quantum fluctuations.
It's
Wow.
pretty amazing, right? Quantum physics isn't just about the very small. It shapes the very large, too. And here's the kicker. It might even help us understand some of the biggest mysteries in cosmology.
Okay, now you're just messing with me, right? What mysteries?
Dark matter, dark energy, the really big, really weird stuff.
Dark matter, dark energy. Okay, now you've piqued my curiosity. What do those have to do with quantum physics?
Well, think about the Standard Model, that framework that describes all those fundamental particles. It's been amazingly successful, but it doesn't explain everything.
And dark matter is one of those things.
Exactly. It's like this mysterious stuff that doesn't seem to interact with light at all. That's why we can't see it directly. We only know it's there because of its gravitational pull on the stuff we can see.
So how does quantum physics come into play?
Some physicists think dark matter could be made up of these, well, exotic particles. Particles that are predicted by theories beyond the Standard Model. Theories like, supersymmetry, for example. And guess what? These particles, they'd still follow the rules of quantum mechanics.
So we might need some whole new physics, like a quantum physics of the very large, to truly understand dark matter and dark energy.
Now you're thinking like a physicist. And it gets even weirder. Lavender talks about this thing called quantum entanglement, and she calls it spooky action at a distance.
Okay, spooky action. You're going to have to explain that one. I have no idea what you're talking about.
Okay, so imagine two particles, not just any particles, but particles that are linked. They're connected in this way that they share the same fate, and it doesn't matter how far apart they are.
What do you mean share the same fate?
So let's say you measure one of these particles and figure out, I don't know, it's spinning up. You instantly know that the other particle, even if it's on the other side of the galaxy, is spinning down.
Wait, hold on. Are you saying they communicate with each other faster than the speed of light? That's impossible.
That's exactly what Einstein thought. It freaked him out, actually. He called it spooky action at a distance because it seemed to go against his whole theory of relativity, the one that says nothing can travel faster than light. He thought there had to be some other explanation, some hidden variable, something we just weren't seeing.
So, was he wrong?
Well, it's not that he was wrong, but quantum mechanics, it kind of throws a wrench in things. Decades of experiments, and we're talking really, really precise experiments, have shown that this entanglement thing, it's real. And there are no hidden variables, no secret signals. It's just how the quantum world works.
Okay, I'm trying to wrap my head around this. It's like if I had two magic coins and I flipped one and it landed on heads, the other one, no matter how far away, would automatically flip to tails.
You got it. It's like they're connected by some invisible thread, even across vast distances.
So it's not just a theoretical idea. Scientists can actually do this entanglement thing.
Oh, yeah. They've done it with photons, electrons, even atoms. And they keep entangling things over larger and larger distances.
Lavender even mentioned quantum teleportation. Is that like beam me up, Scotty? Are we talking Star Trek stuff here?
I wish. Sadly, it's not quite that exciting. Quantum teleportation isn't about beaming matter around. It's about transferring quantum information, the state of one particle to another, using entanglement as the transporter.
So like sending a blueprint of a particle instead of the particle itself.
You got it. And scientists have already teleported the quantum states of photons, even atoms, across pretty impressive distances.
Wow. This technology, it has the potential to change everything, right? I mean, Lavender was talking about quantum computers being able to do things that regular computers could only dream of.
Exactly. Quantum computers, they use these quantum phenomena, things like superposition, where a quantum bit can be in multiple states at once, and entanglement too, to do incredibly complex calculations.
It sounds like quantum computing is still in its early stages.
Oh, definitely. But the potential is huge. It could change medicine, material science. We could be talking new drugs, new materials that have never existed before, the ability to model complex systems, you name it.
Wow. So we've gone from the tiniest particles to the largest structures in the universe, all in one deep dive. It's clear that quantum physics isn't just some abstract theory. It's like the foundation of everything.
It really makes you appreciate how much we don't know, doesn't it? And how much more there is to discover.
Absolutely. And that's what makes this so fascinating. It's like we've just open the door to this whole new world of understanding.
Exactly. And who knows what we'll find as we keep exploring.
I can't wait to find out. This has been an incredible journey. Thank you so much for guiding us through this amazing world of quantum physics.
It's been my pleasure. It's not every day you get to talk about spooky action at a distance.
That's for sure. And to everyone listening, thank you for joining us on this deep dive. We'll keep exploring, keep asking those big questions, and who knows what mind-bending adventures await. Until next time.